Hi everyone, let's continue our discussion of the physical applications of calculus, part 2. So we're going to look at how we can calculate the mass of a disk. Now, a disk is like a filled-in circle. So imagine the circle is filled in all the way. What we want to do is something that's pretty common in our travels in calculus 2, which is we want to associate to each point on an interval a slice or a piece. Okay, and what is a slice going to look like here? A slice is going to be a circle. So we need to think about what would we get out of this circle? So remember that with a rod, we had what was called a linear density function. A disk has what's called a radial density function. That tells you, if you know the radius of the subcircle that you're working with here, what the density is for that little piece. So now let's think about if we had a circle we could basically cut up and turn into a line. And so if we knew the length of this line, then we would be able to know the mass of that little piece, right? So if we're at a point here, x, then the circumference of this circle, this is x, the circumference would be 2 pi x. And so what that means is that the mass of this little piece would be 2 pi x times the density, because mass is always length times density for one-dimensional things. And the radial density function is going to be a function. It's going to change, but let's call it rho of x. So the mass at that little circle will actually be 2 pi x times rho of x. Now, this is for one little piece, and if we want to think about the overall mass, it's all of these little circles having their mass added together. And we're adding together infinitely many small, tiny things like this. That's exactly what an integral is. So the upshot is that the mass of a disk of radius r with a radial density function rho will be given by definite integral from 0 to r of 2 pi x rho of x dx. Now, this is a formula that's pretty straightforward to apply most of the time. Important thing to emphasize here is not just what the formula is so you can memorize it, but also how we got that formula by reasoning through all these little small circles and what the mass of a single small circle would be. So we'll go over some examples now of how we would apply this formula to calculate the mass of a disk. Suppose a manufacturer makes disk with a radial density of rho of x equals the square root of x cubed. We want to calculate the mass of a disk of radius 6. So to start, we'll use our formula m is equal to the definite integral from 0 to 6 in this case, 2 pi x times rho of x dx. Now we can just replace rho of x with the formula. So it's going to be 2 pi x times the square root of x cubed dx. In looking at this, the square root of x cubed is kind of rough. So let's work on simplifying and replacing it. We will use algebra to rewrite this square root of x cubed as x cubed raised to the 1/2, which can then be rewritten as x to the 3/2. Now we can combine those and get 2 pi x times x to the 3/2 dx. And that x times x to the 3/2 can be rewritten using algebra as the definite integral from 0 to 6 of, well, x to the 1 times x to the 3/2 becomes x to the 5/2 because we add the exponents. So this becomes the definite integral from 0 to 6 of 2 pi x to the 5/2 dx. Let's keep going. We can rewrite this and pull the 2 pi in front because it's a constant. And so we have 2 pi times the definite integral from 0 to 6 of x to the 5/2 dx. Now, in looking at this, x to the 5/2 basic power rule. So the antiderivative would be 1 over 5/2 plus 1 times x to the 5/2 plus 1. That's an antiderivative, so that's 1 over 7/2 times x to the 7/2, which we then simplify to 2/7 times x to the 7/2. And I messed this up. If you notice, it should be 2/7 x to the 7/2. So I did it right here. 2 pi times 2/7 x to the 7/2 minus 2/7 times 0 to the 7/2. So this will be 2 pi times 2/7 times 6 to the 7/2. And that will be our final answer. Okay, a manufacturer makes discs with a radial density given by rho of x equals 4x plus 0.12. We're asked to calculate the mass of a disc of radius 200. So again, we have our basic formula, which will be the integral from 0 to 200 of 4x plus 1.2 times dx. Wait a minute. Hold on. Does that look right to you? No, we're missing a 2 pi x times that expression. So make sure you're using the right formula. Remember that here, since we're dealing with radial density, the radius of the circle becomes involved, and we see the circumference of the circle showing up as 2 pi x. Now that I'm sure I have the right formula, I'm going to try to use the computer to type this into Wolfram alpha. So the definite integral from 0 to 200, 2 times pi times x times 4x plus 1.2 dx. That's one of the drawbacks of computers, is they can give you these answers that are rounded or written in scientific notation. I'm going to try this with a different program called Mathematica. So I have 2 times pi times x times 4x plus 1.2 integrated from 0 to 200. It gives me the same answer. When I try to get it to show me all of the digits, I'm struggling a little bit. I'm sure there's a way, but let's just do it by hand. Key here is we will need to distribute this 2 pi x through, so we're dealing with the definite integral from 0 to 200, 8 pi x squared plus 2.4 pi x dx. So as usual, we need an antiderivative of this, and if we look at the x squared, we know that that antiderivative could be 1/3 x cubed. So I'm going to have 8 pi times 1/3 x cubed, and the x could be 1/2 x squared. So this becomes 2.4 times pi times 1/2 x squared. And so this is going to be evaluated between 200 and 0 and subtracted. So this is 8 pi over 3 times x cubed plus the 2 and the 1/2 cancel and give me 4 pi x squared. And I'm going to evaluate that at x equals 0, x equals 200, and subtract. So this becomes 8 pi over 3 times 200 cubed plus 4 pi times 200 squared minus 8 pi over 3 times 0 cubed plus 4 pi times 0 squared. This is just 0, and so my exact answer would be expressed in this form. And I don't have to worry about decimals. I could put this in and see what I get.